Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Brendan Hermalyn. Brendan is a PI at the Institute, and he's also associated with NASA Ames and University of Hawaii. Brendan did a Bachelor's of Science in Physics and Music, and then did a Master's and a PhD at Brown University in Planetary Sciences. Then he did an NAA postdoc at the University of Hawaii, and he's currently associated with the Hawaii Spaceflight Laboratory, in addition to the SETI Institute. His career interests involve instrument development and testing, experimental and computational studies of ejecta velocities and high-speed photogrammetry for capturing impacts into test targets. He's also interested in prediction and hazard assessment for proximal impacts. And he's also been involved in several projects to deploy visible and near-infrared time-lapse systems in the Antarctic and also at Mauna Kea. He's also a PI on the DiscoSat Cubesat mission, and he's recently been a member of the science team on the LADEE and the LADEE and LCROSS missions over at NASA Ames. So today he's going to talk to us a little bit about those missions and what we can learn from impacts. So please join me in welcoming Brendan.
Thank you. Thank you, Adrian. Appreciate it. I'm glad I updated my website recently, so that's good. So it's really an honor actually to be here at the SETI talks. Obviously, there's a reputation for these, extends well beyond these walls. So I'm actually quite happy to be here. To put it in perspective, on the other hand, I also got an email yesterday from somebody I respect at Ames who says, I'm really looking forward to your talk tomorrow. I'm going to be walking my dog during it. It sort of takes me off the mind. So the motivation for this, don't have a laser pointer, do I? Okay, use the mouse. It is truly the future. Well, the motivation for this talk really comes partially from looking at the surfaces of bodies like this, right? This is the moon. I don't think that's going to be a surprise to anyone here. There's craters of all different sizes and scales. The big ones, we got giant impact basins. We also have small ones that are ongoing. We're even seeing new ones being formed by some of the instruments currently in orbit around the moon. And in fact, that's kind of one of the driving questions here. So I have a video. If you take a look, I guess I can't step out of the frame. If you look at the sort of the middle on the right-hand side over there, there's a little flash that occurs. And what happens is when an impact event occurs, some of the energy is partitioned into visible light. And that's what we're seeing here. We're seeing an impact flash. Estimates from the brightness of this is something like a 25-centimeter rock that's going at about 38 kilometers a second. This is part of a study that's being done by the Marshall Space Flight Center, where we're trying to map out how many of these are occurring, when they're occurring, and where they're occurring. And it's not just this one, though. This was one that was all the way back in 2006 when the study started. But these are happening on an ongoing basis. I just updated this slide last night. So since 2005, there have been 319 impacts that have been confirmed by multiple telescopes looking at the moon. You can see these flashes when we're looking on the dark side, right? So without any solar illumination. And you have to be looking at the right place. So when we're lucky, in the last few years, we've seen 319 impacts that are big enough that we can actually see it from Earth. So this sort of changes our concept of cratering as something that's happened a really, really long time ago and is kind of a view of the past to an active process. So not only with that top thing where we're observing impacts on the moon constantly with the Marshall guys, but also things like the P2010 or A2 linear impact, which was thought to be a main belt comet, but it seems that due to some of our impact modeling, looks a lot more like an impact event. And also several of the missions. There's the Deep Impact mission, which impacted Comet Tempel 1, looking for our first view of under the surface of comets. The LCROSS mission, which was to the south pole of the moon, looking for volatiles. We'll talk about both of those in a little bit more detail. And also the Aladdin mission on there, which was competed at the same time as the Deep Impact mission for the Discovery round. And I just think it's really cool. We were going to smash into the moons of Mars and kind of fly past with a Stardust-style collector and pick up some of that impact stuff and return it to Earth. Along those lines, there's actually another advantage to doing impact stuff, which is a pet project, I guess, of mine, where if you impact planetary bodies, you have probably the cheapest access to the subsurface. So for deep impact, we smashed into the comet at 330 million. Putting someone up there with a shovel is somewhat harder and a little bit more expensive. Same goes for LCROSS. Where we really want to be is somewhere in the Cubesat range, right? Where we're talking about fractions of millions of dollars to do it, rather than tens. So the overview of the talk today is, first, why try to understand impact ejecta, which is a question I ask myself on a daily basis. Applications, so impact missions, planetary surfaces, and also some of our future possibilities. I like to start off a lot of these talks by looking at a video here. So this is an impact experiment that took place down the street at the NASA Ames vertical gun range. And I cheated a little bit and backfilled the chamber with a small amount of argon, so it looks a little bit more awesome than normal. But the point here is that impacts are not some explosive event where stuff goes everywhere, but they're actually a very orderly, shock-driven event, where you can see it's an ejecta. This is what we call an ejecta curtain that comes up and then will lay back down. I'll play this one more time. So you can see this was a 60-degree impact to horizontal. And all those particles, you can actually, I was hoping we could turn down the lights a little bit if that doesn't put everybody to sleep around lunchtime here. But you can see those particles as they propagate upward and out. It's really sort of pretty. It looks like a fluid flowing. What we're seeing here has been described for a while. This is where we take an impact event that occurs right on the surface, and we drive material along streamlines down along the crater wall and then up and out. So what we're looking at is stuff that has been excavated from underneath the surface down and out in a fairly orderly fashion. So the questions I'm hoping to talk about today, at least a little bit, are how fast is our impact ejecta? How does that relate to our target properties, so different ejecta patterns and how we can observe different ejecta properties from impact missions? And then also things like hazard assessment. So one question is, how thick does your shielding have to be to protect you if you're going to go sit on the moon for 6 months at a time? It's not going to be a direct impact that gets you. It's going to be all the shrapnel, right? So I don't have too many plots here, but I wanted to discuss this just really quickly. This is a plot of the velocity of the ejecta on the ordinate axis versus the launch position, which is the distance between the impact point and where a particle was launched out of, right? So an xe over r, a launch position, that's the same as the final crater size. That's the last time you'll launch anything. That's how big your crater is. So this is a logarithmic plot on both axes. And what we notice is that from a bunch of experiments, there seems to be a pretty comfortable power law that's drawn, right? It's somewhat reliable. And we can put our little equation on there. But there's a problem with this. And we're first seeing this problem with the LCROSS mission, which is, of course, to take that large white thing, that's the upper stage of the Centaur upper stage that took LRO and LCROSS to the moon, and we smashed that into a south polar region. This particular south polar region was in permanent shadow, which means that any ejecta that was launched, in order for us to be able to observe it, had to get into the sunlight to be able to even see it. So it had to go from permanent shadow. I have a slightly more illustrative slide here, where all that material has to come up out of the permanent shadow to be observed by the LCROSS shepherding spacecraft or by any assets on Earth. The problem is that just to get material above the sunlight horizon for LCROSS puts us into that red range, where we really don't have very much data. And we have to go way further out, right? There's a velocity requirement just to get stuff up 830 meters that we really weren't meeting very well with our prior knowledge. To make this a little bit more visual, if we take a crater like this is a random crater on the far side. It's about 300 meters. If we take that same LCROSS sort of horizon and map it out ballistically, that only talks about the ejecta that's going that far. So it's really not that much, actually, in the grand scheme of stuff. And it's really not the stuff that we're interested in. A lot of that early time ejecta that's going very fast, that's highly interesting because it talks a lot about how the crater itself was formed, the impact parameters and that sort of stuff. Another problem, though, we've been talking a lot about vertical impacts, right? And basically nothing happens vertically on planetary bodies. This is a probability distribution of the impact angle. This is originally actually derived by Gilbert in his landmark study in landmark book in 1893. It was re-derived by Shoemaker in the 60s, and it was the same, so that's good. What we'll notice is that in terms of the probability distribution, almost everything is hitting between, say, 30 degrees and 60 degrees to local horizontal. Very little is hitting at 90, very little is hitting at glazing angle. So this isn't a surprise if you look at planetary surfaces either, because this is just the moon. We have a bunch of different craters that are fairly obviously not symmetric, right? Even though the crater itself is usually circular, or at least symmetric, the ejecta belies the fact that these were coming in at highly oblique angles. So that brings us to this here. The NASA Ames Vertical Gun Range is a facility. It's actually just down the street. I usually have a map on here, but I think a lot of people in the room know exactly where this is. So you just go down there. This was originally developed in support of the Apollo program, just to try and understand how impact processes affected the lunar regolith and how regolith is formed. There was some concern that when you land, you would just start sinking if it was really underdense. So that blue part on the bottom there, that's about 2 meters tall. That's a vacuum chamber. And the gun itself is mounted. You can see it sort of looks like an orange A-frame. The gun itself is a two-stage light gas gun that's mounted on that A-frame, and it's on a Nike missile screw. So it allows it to pivot up and over. So you can shoot into a chunk of material that's normally mounted, which is good if you're trying to study like regolith or sand or some other non-consolidated material, and shoot into it at different impact angles. This is fairly unique. A lot of other chambers are mounted horizontally, which makes it really hard to hold sand against the wall. It falls out. Now, one of the reasons that this facility is still operating is because we keep getting new techniques in there. This has been going for a while, right, since pre-Apollo. So one of the techniques I'm going to talk briefly about that we're using to sort of push things forward at the gun range is particle tracking or particle imaging velocimetry. This is the one slide overview. The concept is very intuitive, I think. If you take one picture and you see a flow field of particles, and you take a picture at a certain time later, you see what the distance they've traveled, you can understand what their velocities are and their locations. So even more visual is if you take a look. This is from a fluidic experiment. Particle tracking is used a lot in fluid type studies. Visually, it's pretty easy to see what's going fast. You can see that there's a little reverse vortex on the far upper right-hand side. There's some boundary layer effects occurring towards the bottom. The trick is to make it something from visual to something that's actually quantitative, where you can get a velocity field out of that. So this relates to our impact stuff, and with two methods. First, we're going to look at vertical impacts to get things started, and then we're going to look at a slightly harder way of doing it with oblique impacts. This is, I think, one of the first times we've been able to measure the impact ejecta in a time-resolved fashion coming out of these craters. So it's pretty cool stuff. So the schematic for the setup here, remember this blue thing is our vacuum chamber. We have a bunch of cameras all over the place. We've defined a sort of measurement field here with a very narrow depth of field. So we said long focal length lenses, wide open. And the concept here is that the projectile will come down and start forming an ejecta curtain as we see, but we're only going to look right along the side of the curtain and just track those particles. So what this really looks like is this. This is an impact event. This is a 5.5 kilometers a second impact, vertical, of a 1/4-inch aluminum projectile. I'll play it again because it sort of, you can again visually just see those particles coming up and out of the crater. So we track those particles in very high time resolution, and we're able to do a little bit better than that first slide that I showed you. So that was where that first slide cut off with that red bar. So everything to the left of that is new stuff. So there's a couple of takeaways here. First, looks an awful lot like if you just continued the line, it would keep going, right? So we wonder why you had to do this. Have a good answer for that. We're not actually very interested in the launch position. That's not a really good parameter to look at if you're concerned about actually replicating an impact event, or if, even worse, if you're going to go and look at one, like with LCROSS. Because knowing the launch position is not very physical for us. Knowing the time of launch is much more physical. So in addition to being able to make the one plot go a lot further along the exact same line, we're able to measure this as a function of time, and that's the plot down here is still velocity on the left-hand side, and on the abscissa, that's a time axis. So knowing as a function of time what the velocity of eject is quite important for understanding our impact mission stuff. The other thing we are able to look at is the time-resolved ejection angles. A lot of people considered that this was sort of an over and done story. Everything seemed to launch at just about 45 degrees. What we're noticing is that not only is there a considerable disparity at early times, where things can come out lower by up to 10 degrees lower, they migrate through the cratering process. So it doesn't sound like all that much, but if you think about a 10-degree difference in ejection angle, it actually means quite a bit if you're talking about ballistic distance on the moon. Going back to here, though, we haven't yet captured how things work with oblique impacts. So to do the oblique impacts, it's a little bit more difficult. What we use is a laser light sheet that's projected inside of the chamber with multiple cameras up top. Could I ask that we kill the lights for this one too? Because I did this and I can barely see it. So, all right, here we go. So the concept here, once again, the projectile comes down from the top, and the ejecta comes up and out. But it's illuminated by this laser light sheet. We don't look at it from the side, though. We like to look at it from up above. And you can see even in this animation that particles will enter the light sheet, move in and out of it, and be captured for 1 or 2 frames of our camera, and then progress on. So the way we do this at the gun range, this is to sort of show you, we have a series of high-speed cameras. In this case, we're using 4 of these. These are shooting at 20,000 frames a second. And this really looks like this, where we have, these should loop a couple of times. This is a 30-degree impact. So you can already see the asymmetry forming in the ejecta curtain, right? Especially at very early times, where material is coming up heavily biased downrange and going very, very fast. So the technique uses a snapshot of 4 cameras. So just to clarify, what we're looking at here is just 1/2 of that ejecta curtain from up top from different angles, right, from the different cameras. And the difference in how the ejecta curtain looks, that's all due to our perspective view. We use that to our advantage in a computer vision type technique, where if you look from one camera, you don't really know where it is in one direction, right? You know where it is in 2 directions, but not where it is in that third. But if you use 2 cameras or even more, you can sort of get an idea, if you're looking at the same particle from multiple cameras, mapped along what we call epipolar lines, you can get an idea of exactly where those particles are in 3D space. So as a result of that, we have an image not of just the particles from the top, but kind of an idea of where it is from all 3 directions. So this is highly exaggerated in the Z direction here. That's only about 10 millimeters in Z. But we get a pretty good idea of where all those particles are. So this is exciting. We have the first sort of method of getting after a time-resolved estimate and measurement. I'll say measurement, right? That's what you say to your funding agency. It's a measurement. Measurement of the ejecta velocity from oblique impacts. And we can start to actually apply that. Talk really quickly about some of the results from this, and then I want to start talking about how we can actually apply it to planetary surfaces and also to some of our impact missions. So what we'll find is for a 30-degree impact, oh, you can't see me when I circle, huh? 30-degree impact, if we divide this into 2 components, the downrange component, which is in the direction of the impact, right? So if you have a 30-degree impact, the downrange is down over here, and the uprange component, which is opposite that. What you'll notice is that the downrange, that's the blue stuff on the bottom, that's coming out at very low angles, and it's coming out at very high speeds. This is intuitive in many ways, right, in an impact event. But this is the first time we're able to actually measure that as we progress through the cratering effect. The uprange direction actually comes out sort of the opposite, at very high angles and at relatively low speeds. So understanding how this sort of maps out onto the planetary surfaces that we're going to be looking at, pretty cool. We can do this, of course, not just for 30 degrees, but for over a range of impact angles, all the way up to the axisymmetric 90-degree impact. So now we're on to prospects, or the why we should care. And sometimes at night I look at this slide also. It helps. So the first one is planetary impacts. We don't want to just get caught up in the measurement, but also sort of step back and think about how this looks to planetary implications. Planetary impacts, we're going to take a look at some of how we can take a look at those images that show obvious asymmetry in our ejecta patterns, and then actually see if we can back out some of the information about the impactor itself, which would be kind of neat. Second one is missions and interpretations. I have 3 missions I'd like to talk about briefly that have used some of this data and hopefully will continue to. And then our future possibilities, because I feel like we should all have a pet mission that we'd like to do if we're working in this area. The first one is to talk about these planetary impacts. We wanted to talk about the target properties. We've done some other testing beyond just those first few frames that show that there's a really big difference between different target materials. So if you're impacting into, for example, a regolith material versus a sandy material, or a ice consolidated sort of regolith material, those all look very, very different. And they look particularly different if you look at the rightmost plot there in our ejection angles. So things that are the blue, excuse me, I'm sorry this is so hard to see here. That green stuff, that's all from a consolidated sand block. We welded this together as a proxy for ice welded regolith. So if you're going to impact somewhere like, for example, somewhere in the south pole of the moon where you might have regolith that is so bound that it actually acts sort of icy, might expect to see something more like that. On the other hand, if you go down to unconsolidated materials, that red stuff is sand. Sand has been used for a really long time as a proxy for impact material because when you think about an impact event on a planetary scale, the shock wave is very, very strong. What will happen is it will crush and commute material. Even if you hit basalt, it will crush material to well beyond the size of the final crater. So you're essentially crushing all the material and then excavating it, kind of like sand. So we use sand quite a bit. The problem is that we haven't really calibrated that against a lot of regolith-like materials, and that's what that blue stuff is towards the bottom. That's a regolith proxy. It's not like JSC1A or any of those regolith analogs. We find that those are actually really pretty terrible in terms of material properties and impacts. You don't make craters that look like craters on the moon. This is the best thing we've been able to find. This is called airfall pumice dust. So it's not a block of pumice, but it's actually pumice that fell out of the sky, and it comes in these very agglutinitic little particles. And it exhibits a lot of the same material properties as lunar regolith, right? Where you have these agglutinitic little glassy particles that have a high angle of repose and really have a lot of internal strength. So by taking these sort of measurements, we have a bunch of others, we're able to start building up what you'd expect a ejecta curtain to look like if it impacts into different stuff. So the sand canonical sort of view looks like one thing. If it's porous and compressible, kind of closer to a lunar regolith, you tend to have wider ejection curtain because of the lower ejection angles. If it's hard or ice welded, it kind of looks very narrow. And if it's layered, it does this sort of inverted sombrero hat kind of thing. With oblique impacts, this shows up even more strongly. So these are identical 30-degree impacts into a pumice target. That's, again, that airfall pumice dust, which is a proxy for regolith material. And perlite target, which is, I think we actually got this at Orchard Supply down the street and sieved it. But the perlite target is really good for, say, a cometary analog or an asteroid, where you have a lot of big blocks but very weird strength properties. And you can see just that uprange zone of avoidance. That's where we have those curves marked out. Those look very different even for identical impacts. And of course, this happens on the moon as well. The farmost right slide there, that's Jackson Crater on the far side of the moon, where again you can see, and the impactor came from the top left-hand corner. You can again see those uprange zone of avoidance curved rays that appear. Well, we see it in our impact experiments as well, right? We can actually track that zone of avoidance for one of the first times as the crater forms. And we can take that data and start to form different types of ejecta curtains. So here we are, we're looking at that same Apollo 15 image that we saw a little bit earlier. This is a pretty small crater, but you can see that in the uprange direction, opposite of the impact, there's a zone of avoidance. There's no ejecta, right? The trick is to try and figure out physically, why is this particular impact, why does this not have ejecta while other impacts of similar size do in the uprange area? And more importantly, what does the curvature of that ejecta look like? What does that mean physically? So we've been able to sort of get pretty far along on this. This is an ongoing project, but we've been able to tune the different strength parameters and the compressibility of the target to start to actually get at the physics of why some of these look like they have very curved uprange rays. Some of them look like they don't have any curvature at all. Some of them don't experience the uprange zone of avoidance very much at all. So you can see we have going through the A there, that's much like sand. You wouldn't be able to actually see very much of this uprange zone of avoidance. The curtain closes very early. If you have a lot more porosity and a little bit of strength, that's closer to what we'd look at for lunar analog type material. You can see that the rays are actually pretty straight, and you get this nice big zone of avoidance. And then that thing over there on C, where it looks very, very curved, that seems to happen a lot for very low density and fluffy type materials. And in fact, that's exactly what we saw with the Deep Impact mission. So the Deep Impact mission is where we hit, or I'm segueing seamlessly into our mission type talk here. We impacted comet Tempel 1 at about 30 degrees to the local horizontal. And the comets, we didn't really know what they were, but we are pretty sure now that this is a pretty low density to fluffy type materials. And we were going at a pretty high impact speed. So a 30-degree impact, pretty high speed at 10 kilometers per second. So taking all of our results out of these different impactor target materials that we've been studying at the Ames gun range, we're able to sort of predict what the uprange zone of avoidance would look like. So I have 4 simulations taking our experimental data and extrapolating it on the left-hand side, and 2 actual frames from the Deep Impact spacecraft, which viewed the ejecta curtain. Again, we could do without the lights, but down here, this is a test of your visual acuity more than an actual talk. I just want to make sure we're clear. So the impactor came basically from where you're sitting now. It's highly foreshortened along our trajectory here where our look angle is. And those uprange zone of avoidance actually shows up pretty well in both of our simulations there. So another mission that actually is pretty related to how we understand impact ejecta has been the recent LADEE mission. We have several of those people here. The LADEE mission was searching for dust and other volatiles in the tenuous lunar exosphere. And the component that I was working on was the ultraviolet and visible spectrometer. And what we did with the spectrometer is we would go, this is in a retrograde equatorial orbit, and those bars that you see, particularly that blue one, denotes the field of view of the spectrometer. So we were on as we would cross over the terminator and go into lunar night, and of course when we came over on the other side as well. So this is all great, but if you think about not only the contribution of the micrometeoritic material, but also these larger impacts, and we know that they're happening, right? The Marshall guys keep measuring that we keep on having this constant influx of relatively large impacts. These things are all forming, craters that are, this big or larger. So we should actually be able to predict how many of those we would be able to see launched into our field of view with LADEE. And analysis is still ongoing, but the concept is, of course, where if you have an impact event occur, and there's LADEE, you can see it, it looks like LADEE. If you convolve that with our field of view, there's a pretty good prediction of how much stuff you should be able to see and how often you should be able to see it. And lastly, I want to talk a little bit about our LCROSS mission. LCROSS was kind of a weird mission from an impact standpoint. We were using a hollow, very low density, irregularly shaped object. This is the Centaur upper stage. Its relative density, even though it weighed quite a bit, its relative density was extremely low. It was going relatively slow, only at 2.5 kilometers a second, compared to, much, much faster than that, usually 12 or so plus on the moon for average impact velocity. And we didn't really even know what we were going to hit into, right? Because we're going into a permanently shadowed region, which was not really imageable. So, of course, the LCROSS mission, a lot of the motivation for this came from trying to understand what was in these south polar deposits that seemed to exhibit an enhanced signature that would be consistent with water ice or anything else that's hydrogen bearing. So I'm going to skip through this real quick, just to in case we've sort of forgotten about what we're looking at here. This is a view of the south pole of the moon, and a simulation over a certain area, a certain amount of time. You'll notice that there's portions of this, because we're on the south pole of the moon, the sun angle is very grazing. And there are areas in here where if you make a big hole, a big crater, the sun never actually reaches the south pole, the bottom part of that crater. As a result, we get these areas that are essentially permanently shadowed, at least over the timescales that we're caring about right now. Now, the LCROSS mission was trying to take advantage of one of these first slides I was talking about, where if you impact something, it's not just some big random explosion, it's that you're driving material out from under the surface and driving it up into a place where you can actually measure it, right? So that was exactly the concept. We wanted to see what was in these south polar deposit regions. We wanted to drive that material up and out so we can actually measure it for the first time. So we did that. This is a freeze frame, one of the images from the LCROSS shepherding spacecraft. The Centaur impacted, and of course there was another spacecraft that followed it down, imaging it and taking a whole lot of spectra. And inside of that, this is also, it was kind of a weird image from the moon because you were looking basically up at it from the bottom. You can see we impacted into the Centaur crater region, that PSR region, that cold dark black area, and we got an ejecta curtain that came up and out. But that ejecta curtain didn't look like what I was showing you before, right? It looks more like a big blob. It doesn't look like this very nice inverted lampshade kind of thing. And it also acted a little bit funny in that this is a plot of where we're looking at the spectrometer signal from both the ultraviolet and visible spectrometer and near-infrared spectrometer. What you'd expect to see is that the ejector would come up, be up there for a few seconds ballistically, and move out of the field of view of the spectrometers, and then fall back down to the surface, and so it would be a pulse sort of response. Instead of that, we saw this very continuous response after a pulse that we weren't really necessarily going to expect from canonical models. Our visible camera also showed that there was a persistence in ejecta for much longer than we expected. Well, we were kind of taking advantage of the Ames gun range again here, where we were trying to figure out what was going to happen if we used this really weird impactor. So we used some of the LCROSS engineering units and flight spares. And it turns out if you look at the Centaur upper stage, despite it having really weird geometry and a weird mass distribution, most of the mass sort of lives in this spherical tank, which is the spherical steel tank, and everything else is kind of just the fluff around it. So we did a series of experiments to understand what would happen if we used these spheres that were not only solid but also hollow, and understand how that failure mode might project itself into the ejecta current. So I have a couple of high-speed videos here. I have a solid impact on the left-hand side and a hollow projectile that is the exact same size. These are at our LCROSS velocities. I want you to play these a couple of times. One thing that we noticed almost immediately is that while the solid projectile makes a nice-looking ejecta curtain, the hollow one has this big honking thing that comes coming out of the center that seems to fill in the ejecta curtain. I'll show that one more time. So the failure mode of the projectile is actually really important in understanding what our impact ejector would look like, and also where we're measuring it from. Slightly different view of this. This is at a slower frame rate than that first one. That first one's at 500,000 frames a second. This is at only about 9,000. You'll notice that that center portion of the curtain is really well filled in by this highly collimated high-angle jet of material that's just coming out. It's actually coming out at very high speeds and coming from relatively deep within the crater. And when we went into the chamber, we went inside that blue thing and looked up, and we saw that it got plastered all over the top of the vacuum chamber. So it's coming out pretty quick. We were able to measure it. It was coming out at around 1.5 kilometers a second, possibly a little bit faster. So the projectile, of course, came down this way. So it's coming straight back up the pipe. So, and then we got to remove this. And by we, I mean I got to scrape this off the top of the chamber. So this actually worked really in our benefit for LCROSS because it preserved a very long duration signal of material that was coming out of the very deepest portion of the crater that we excavated. So now with a few minutes left, I wanted to talk briefly about a hypothetical case. LCROSS was really cool in that it provided a single point measurement that was able to show us, indeed, there was a significant amount of water in these hydrogen-rich regions on the south pole of the moon. But we sort of need more than that to go forward. And one way to do this is instead of sending extremely large impactors, maybe send a series of very small ones. So I have a hypothetical case where we've been doing this for a while. This was funded by a Keck Institute study, and we're always happy to take any study money to do that, right? So at 2.5 kilometers a second into the moon, what could you do with Cubesats? And in case not everybody is familiar with Cubesats, this is really just describing a form factor of relatively small satellites. A 1-unit cube is 10 centimeters by 10 by 10, very small. You can go up in some degree to the size. You can do a 3-unit or 6-unit, start to get to slightly larger form factors. But these are remarkably capable small satellites. I think the form factor was originally developed. I forgot who it was, but I heard somebody say, well, we wanted to make a form factor where nobody would be able to get into trouble with these. So we make it so small that it'll like barely work. And as a result, now we have hundreds of these have launched. They're extremely capable, and a lot of the tech has sort of caught up with it. So here, I stole this from online. I don't know who that kid is, but that's to give you an idea of the scale of a 3-unit CubeSat. And they're launched out of that thing on the bottom right-hand corner. That's called a P-pod. And that's sort of the cost savings of the CubeSat is that you don't have to pass quite the same level of qualification as a secondary. You just throw it in this thing. That is well qualified. You can disintegrate if you like, but it's not going to harm the main primary payload. So because we have all these primary payloads going up with a lot of extra mass capability, it's great that we can throw these small secondaries on and do even more science. I think this is going to be a really important thing, not only right now, but in the future, as we move forward trying to do cool stuff in space. I have a small plug in the upper right-hand corner. That's our mock-up of the DiscoSat 1, which is a Cubesat, the Pion. We're looking for, basically a lot of flying aerogel. We're looking for debris in low Earth orbit, trying to figure out exactly how much it is in the sort of small fraction that we can't detect optically or with thermal imaging. Actually want to see it in situ. and see if it's nodal, see if it's coming from different directions. Just thought I'd throw that in there since we were talking about Cubesat. And here's a image that's far too cool not to show. This looks totally fake, but we're also launching these out of the International Space Station. There's a bay on the door where we lock down, and we're able to launch CubeSats right out of the airlock, and then have the astronauts take extremely cool photos for you of your CubeSat flying. That is real, believe it or not. That's real. I think the Planet Labs guys actually are launching quite a bit out of the ISS. There's a disadvantage in that because the ISS is at a particular altitude, you don't have a really long orbital lifetime, because usually a lot of these don't have a lot of propulsion. So they don't last necessarily very long, but if you don't care or you're trying to do an atmospheric study, that's okay. So our mission concept for the lunar impacting, you want to use these small kinetic impactors to excavate material from the subsurface, and then you want to analyze it in a time-resolved fashion, much like LCROSS. So it's sort of mini LCROSSes all over the place, but not only super cheap, but extremely super cheap. The kinetic impact with really small spacecraft actually might be providing a new paradigm for a lot of high-value, very low-cost subsurface access. Just hit everywhere you can. And the interest is coming from a map like this. This is from the Page et al. Paper. And this is a map of ice stability in the lunar south pole as a function of depth. And that color bar on the top is our depth in meters. So anywhere where you see anywhere where you see any color at all, the maximum value is 1 meter. So as long as we can get down a few centimeters to tens of centimeters and be able to excavate that material up into the air, not in the air, above the surface of the moon, and be able to measure it, then we're doing a really good job of accessing the subsurface. If we do that at multiple points, we can start to understand a little bit more of the physics of how ice is getting stuffed into these very cold regions. LCROSS hit the area where if there was going to be ice, it would be there. We want to understand where it is, maybe if there's not ice there or there's not ice here, why is that? So we can understand a little bit more where to go with humans or rovers. So with the Mission Design Center at Ames, we cooked up this trajectory. We did a number of trades, but we were able to find that with a 6-unit CubeSat, which is about the size you need to get under a meter in terms of the size of your crater, the 6-unit CubeSat, where one impacts and another one follows, we could do this for relatively cheap. The whole mission with a bunch of these could be done for, a bunch of these meaning 6 separate impact events, be done for on the order of about 20 million or less. And it can all be done with stuff that we already have. We can more or less get it off the shelf. As soon as we get out into Earth escape, you can just sort of take a slow orbit where you are in essentially an Earth-Moon orbit and then impact the south pole of the moon for pretty reasonable values. How much stuff can you see? This is a cratering question, right? Is how much stuff are you going to see and from what depth? What we're looking at here are 2 plots of the cumulative mass above a given height at different height levels. On the left-hand side, and this is as a function of time, on the left-hand side, this is a 1-unit CubeSat. It's really small. What you notice is that it's really probably not enough, right? We're only looking at the best, if you're looking just 50 meters above the surface, you're only seeing like 80 kilos of material. That's really not very much. But as you get to a 6-unit CubeSat that maybe weighs a little bit more than you'd expect, but 6-unit in size, then we're doing much better, actually. We're getting in the few hundred kilo range. That's the sort of stuff that we can measure with some relative ease, just given our instruments array. So again, this is our sort of concept. As usual happens, science instruments get one portion of this and everything else is spacecraft. But just with given a couple of science instruments and impacting into a couple of different areas where some are always in shadow, some are mostly in shadow, some might have shadow every once in a while, and impacting into a hot area, we'd be able to sample a whole range of very interesting thermal areas on the moon and understand sort of where the provenance of this water ice and other volatiles are. So with that, I'm going to throw up the slide that the Keck Institute paid for. And so it looks really nice, and ask you guys if you have any questions. Thank
you. Brendan, if I could kick off the questions, and if you have a question, put up your hand and I'll get around to you. So you mentioned the LADEE mission, and you mentioned the recent 300 or so impacts that have been able to be seen.
Right.
Has LADEE been in a position where they could view any of those impacts, view variations in dust amount over the surface due to impacts?
Really, really good question. You're asking me with the person who is staring me down the pike from the LADEE mission here in the room.
We can get his comments as well.
I'm sure we will. Anytime that those guys detected an impact flash on the surface of the moon, we were told, and we looked through our data and tried to find it. We have not released any of those details yet, so there's been nothing released. However, I think I can say there's been some presentation of one of the larger impact flashes actually was re-imaged with LRO, the narrow-angle camera on the LROC, and they were able to actually see the crater that formed from this flash. So we actually have a really good constraint. I'm not sure if that paper's out yet, but it should be coming out soon. It's pretty cool.
Yeah, I missed something that connects the launch from something like the ISS and then getting it out of low Earth orbit and to the moon. How do you do that?
Good question. So you missed it because I didn't really say it, right? We assume that we can get to an Earth escape, and once we're on Earth escape, somewhere in that vicinity, then it only takes that amount of delta V to get out to the moon and impact. So going from the ISS, that's probably not possible. That would require a huge amount of delta V, right? It's like 3 kilometers a second, something like that, to get us there. But if we can hitch a ride, and there are several spacecraft that go past Earth escape, and several coming up in the next few years, where as long as we can hitch a ride, we're there. So it's a mission of opportunity going along with the right primary.
What happens if you impact just solid rock? Because you presented mostly sand and fluffy material. Is there any significant difference if you hit solid?
Good question, of course, and the answer is yes. It looks quite a bit different. The closest thing would be that welded target that I showed that had extremely high ejection angles and very low velocities. But impacting into solid rock experimentally is not as interesting for us if we're trying to simulate larger events on planetary bodies. And the reason is because our impact is much smaller, the shock wave is not as strong. So it will not commute material to very far out. And it's perhaps not terribly realistic if we're looking at going from something very small into basalt in the laboratory and going to something that's very big into basalt on the moon. So that's why we like to use these other proxy materials. It's essentially pre-stressing the target. So does that answer the question? Kind of. All right, that's better than I was hoping.
Brendan, for your DiscoSat concept, that was interesting, and I'm assuming you're not returning the aerogel with the sample in it, right?
That's correct.
So can you just say a few words about what instrumentation you could include in that Cubesat to do your science?
Sure. I should sort of clarify, this has actually been already selected for a launch through NASA's Lunar program, so we're in the process of building this right now. So it's a set of photogrammetric cameras that sit behind the aerogel, and we're looking at the streaks. I don't know if you guys have seen the Stardust return, but the Stardust aerogel, which was scooped up parts of a comet tail, these have sort of streaks that go into the aerogel. What we're trying to do is image that with multiple cameras from behind, so we'll be able to detect how long the streaks are and what their direction is. And then that's what gets returned, is the images. So no, we can't return it. It would be really cool. Just imagery. Yeah, yes, it's just imagery. No, we don't have a spectrometer on it. No.
How do you get any kind of composition? I thought you were indicating you could tell what that material was.
No, hold on. No, we don't have any compositional information. But you can probably tell what the velocity is. And if it's coming in at 70 kilometers a second, it's probably not space debris. It's probably something else, right? Yes, sir.
Hi, so I was wondering if you could talk a little bit about your camera and lighting systems. You're obviously shooting, looks like thousands of frames a second. Looks like you have pretty good spatial resolution and would appear to be very little motion blur.
That's
so
right.
maybe you could talk a little bit about how you do that.
Absolutely, happy to. So we have a lot of cool stuff over at the gun range, ranging from a couple of cameras that can shoot up to 1 million frames a second. And at 1 million frames a second, 1 over the exposure time on that is fairly short. So we don't have a lot of motion blur with that. A lot of the other systems we use pulsed lasers, which have 3 nanosecond pulse widths. And we sync those to the camera, so the camera exposure is actually relatively long, and we pulse the laser in between. Sometimes we'll do, if one problem that we've had is we have to pulse the laser twice just to get enough light. So that's usually how we go. We have a suite of cameras. Some of these we're operating with, I think, 8 or 9 cameras all at once. Some of them sync to different frame rates. Really, this sort of technology, even though film cameras existed that were going at 1 million frames a second back in the 60s, and there's some interesting work done on those, the new stuff that we can do with these digital cameras is really pretty remarkable, and I think pushing us forward in terms of what we can measure at the gun range. We can do the same experiment we did 40 years ago, but see totally new stuff.
Last question.
Thanks. You showed us hollow impactors and solid impactors. What about impactors with like a high percentage of void space, like maybe 30% or something on those range?
That's a really good question. You know, we can let me answer it this way. Because of the way the gun is set up, we can basically launch a lot of different stuff. We're not required to do something that's electrostatic, like a nanograph, or something that is ferric, so we could very well launch something like that. Probably we can only go to so low of a strength, and then you are doing a pancake by the time you get to the radiation. So we've done a couple of studies where we vary the amount of hollowness, like the thickness of the wall, and also different stuff. Like the nylon projectile versus stainless steel versus but yeah, I interpreted that it's slightly different. That actually is pretty close to what we look at with the Cubesat. We look weird, right? Try to hollow the side and has a weird value box. Good question.
Recent analyses have shown that thermal cycling on asteroids it creates a lot more regolith by factors or even perhaps orders of magnitude than impacts. If you are planning to do analysis on asteroids, how do you simulate that type of, or how different is that regolith compared to the one created by impacts?
Good question. I think that, and this is a little outside of my field, but if we're going to have impact events, you're going to get much finer particles in chocolate heat versus the thermocycle is my understanding is it won't produce as much of those very, very fine particles. So you'll get more of a gravel pile, which is, I think, the current understanding. It also makes it weirder because if you're impacting into gravel with something that's on the same size as gravel, that sets up a very different impact parameter. It's sort of a bowling ball problem. So that's my best guess.
Okay, Brendan, we have a special SETI Talks mug. It has a lot of void space in there, but I'd encourage you not to use it as an impact generator, if at all possible.
Thank you so much.
But please join me in thanking Brendan for his great talk.